Hello, I'm Dr. Alla Kammerdiner. Welcome to Discrete-event simulation. This is Lecture 6, Fundamental Simulation Concepts. We will continue talking about probability and statistics in simulation. Specifically, I will talk about statistical analysis in simulation and simulation in arena. Statistical analysis in simulation. Recall that we talked about using random input in a simulation and therefore getting random output. So the random input and output data should be analyzed using statistics. We will use what we learned in previous lecture, Lecture 5, to analyze random data. Example 1. Consider a random variable with a probability mass function. It has three values: -1 with corresponding probability 0.25, 0 with corresponding probability 0.5, and 1 with corresponding probability 0.25. We want to be able to plot the probability mass function, which we already did in Lecture 5, find the distribution function and plot it, which we did in Lecture 5. And now I will also show you how to find the probability of variable x that is between -2 and 0.5, also compute the expectation and the variance of x. So recall what we learned in Lecture 5. We can compute the mean for discrete variable using this formula, and for continuous variable using this formula. And also, we know how to compute variance in both cases, and that's using this formula. So variance, of course, is a matter of dispersion around the mean. So let's go back to the example. So to find this value of the probability that x is between -2 and 0.5, we need to notice what are the values of x. The x takes three values, -1, 0, and 1. Now, let's look at values of x that are exactly between strictly less than -2, strictly more than -2, and strictly less than 0.5. Well, there's only two out of these three values that really satisfies this condition, and that's -1 and 0. So, to find the probability that x is between -2 and 0.5, we just sum up the corresponding probabilities of the values that satisfies this condition. So we sum up probability of -1 and probability of 0, which are 0.25 and 0.5 correspondingly. So that gets us 0.75. So now we can also find expectation of x. We will use this formula where we sum up the products of the value of x multiplied by the corresponding probability. So together we have three different values. So we multiply -1 by its probability 0.25, we multiply 0 by its probability 0.5, and we multiply 1 by its probability 0.25. These are the only values that x takes. So we sum these products up, and we get -0.25 for the first product, we get a 0 for the second product, and for the third product we get 0.25. When we add 0.25 to the -0.25, we get 0, so the expectation of x is 0. Now we can find variance. We use this formula, and since the expectation of x is 0, it simplifies to just finding the expectation of x squared. And this is how we can find it. We again using the formula for expectation, we just take it as an expectation of x minus 0 squared. So again, if we look at x value of -1, -0, and then square it, we also multiply it by the probability of -1, which is 0.25. And then 0 minus 0 squared, which is 0 squared, multiplied by the probability of x taking 0 value, which is 0.5, and then we also add the value of x being 1 minus 0 squared, so that's 1 squared, multiplied by the corresponding probability of x equals to 1, which is 0.25. So of course the middle product is again 0, and because minus 1 is now squared, we'll get 0.25 for the first product, and again 0.25 for the second product, so together we get 0.5, so the variance is 0.5. Now let's take a look at the second example where we have x being a continuous random variable with the following density function. So here notice that c is a parameter, it's a constant, and we don't know it, so the first task would be to find the value of the constant c. We also want to be able to plot the PTF, and that's something that we already considered in lecture 5. And then find the distribution function and plot it. You'll find the f of x, and you already know how to plot it because we plotted a similar thing in lecture 5. You'll find probability that x is between 1 and 2 strictly. You'll find the expectation of x and the variance of x. So again, this is a little different because it's a continuous random variable. So let's go ahead and do that. To find the value of constant c, notice that it's true for any density function that when we integrate it over the entire real line, we'll get 1. But this function is defined for x more than 0, so we only need to integrate from 0 to infinity. So using this, we integrate and we plug in our value of f of x, and that leads us to c over 2, which is equals to 1. And so we use this equation c over 2 equals to 1 to find that c equals to 2. Now we can find the distribution function f of x. So the capital F of x, which is a distribution function, is given by this formula. Again, in general, it would be starting with minus infinity to x. But because our function f of x is defined on for x more than 0, we integrate from 0 to x. And we integrate fy dy. Where c, we now already know that c must be 2, so we're going to be using c equals to 2. Because if it's not equal to 2, it would not be a proper density function, because it wouldn't satisfy the condition that integrating this function over the entire line would give us a 1. So now, using this, we integrate again to find the distribution. So we integrate, plugging in the value of f of y, we simply replace the x with a y, and we replace c with a 2. And so we integrate from 0 to x twice exponent of natural exponent of minus 2y dy. And so we'll get this value, right, where we need to evaluate at x and then at y equals to 0. And so when we plug in the values of y equals to x and then value of y equals to 0, we get 1 minus exponent natural exponent of minus 2x. And so that is our function f of x. Notice that again this function is defined for x more than 0. So now, and it's 0 otherwise, which means it's 0 when x is less or equal than 0. Now let's compute the probabilities that x is strictly between 1 and 2. Again, to do that, we just integrate, but rather than integrating from 0 to x, we're integrating from 1 to 2, which are the conditions here, right? Because the x is exactly between 1 and 2. So we integrate from 1 to 2. The function fy dy, we plug in again the value of c equals 2, And when we integrate, we get the answer e to the minus 2 minus e to the minus 4. So now in example 2, we also were able to find the f of x, and we now want to find the expectation of x. So the expectation of x would be from 0 to infinity to y e to the negative 2y dy. And so notice, right, that we used the expectation formula here, but this is a little difficult in terms of the integral, so to solve this we need to use integration by parts rule, which is given here, right? So for this specific case where we integrate from 0 to infinity, the integration by parts rule says that if we have two functions u and dv, we can then compute the integral of u dv from 0 to infinity as u and v evaluated at 0 and infinity minus integral from 0 to infinity of v du. So v using this was u being minus y and v being e to the negative 2y, and then in that case the du is of course minus dy and the dv is minus 2 times e to the 2y. And here the expectation now becomes this integral from 0 to infinity that you can see, and then we're rewriting this as using this integration by parts rule, right? So you can see that already written using this rule in this line here, and then we simplify. So this simplifies to 0.5. So the expectation is 0.5, which if you check what we learned in lecture 5, that exactly corresponds to what we would expect based on the formula, more general formula for exponential distribution, because this is an example of exponential distribution. So now let's take a look at how to compute the variance. To compute the variance, we simply use this formula here, and because we already computed e of x, we just square that. So you can see we have minus 0.5 squared, right? We just squaring the expectation, which is we just computed to be 0.5. And in the first part, you can see the integral from 0 to infinity y squared, and then the f of y, right? So the 2 e to the negative 2y, it's a f of y dy. And that's exactly the expectation of x squared. So again, right, this looks complicated, and to solve it, we need to integrate by parts twice. So I'm not gonna show that, but you can actually do that similar to the expectation. You just need to integrate it twice. Now let's talk about covariance of two random variables. So we learned about covariance in lecture 5, and this is a formula for it that we learned from lecture 5. And it can be also simplified, and so sometimes it might be easier to use the first formula, and sometimes it might be easier to use the second one. And of course, covariance is a measure of linear dependence between x and y, just as the correlation is. And this is a formula for the correlation. So you can see that it depends on covariance x and y, which is in the top of the fraction, and in the bottom we have a square root of the variances. So now let's take a look at some of the definitions in terms of correlated and uncorrelated variables. And these are the definitions that we learned from the previous lecture. So we know that if covariance is 0, the variables are uncorrelated, but they don't have to be independent, right? All the independent variables are going to have covariance 0, but if covariance is 0, it does not mean that we have independent random variables. So let's take a look here at this example where we actually will apply some of these ideas. So in this case, we have x and y that are two discrete random variables with a joint probability mass function. And so because it's a joint probability mass function, it actually has two values, the value for x and the value for y. So this is the first row and this is the second row. And so these two rows define the joint probability mass function for x and y. So we want to be able to find the probability mass functions that are individual for variables x and y, and also there's corresponding expectations and variances, and also be able to find the PMF of xy. And we need the PMF of xy to be able to get the covariance. And so from the PMF of xy, we also want to know the expectation of xy. And if we have that, we can find the covariance xy by that formula that we just reviewed. And of course the correlation by the other formula that we had seen. And we can also answer the questions of whether x and y are uncorrelated, negatively correlated, positively correlated, and we could check their independence as well. So in this case, we first find the PMF of x. So to do that, we need to figure out how many values x takes. X takes only 3 values, and the specific values are -1, 0, and 1. And here how we can compute them. So for each of the values, we need to compute its corresponding probability. So the probability of -1 can be computed from the joint PMF. And the way to do it is just to look at all other possibilities, right, for the joint PMF to have -1. Notice in this two rows above, in this definition of example 3, we have P of -1 and then -2, right? What does it mean? It means that it's P where x is -1 and y is -2. But there's also, right underneath it, there is also P where x is -1 and y is 2. And these are the only joint probability mass functions where x is -1. So we sum those up together, and both of them are 0.125, so we get 0.25. So in a similar way, we can compute the probability of a second value, which is 0. We just notice, we look at the PMF, and we notice where we have the PMF P, x, and y, where the x is 0. And these are two. They're in these two rows. There is a second P, PXYs that are given in these two rows. So you can see the only two values where x is 0 is P0 -2 and P02. And so we sum those up, and they're both 0.25, so we get 0.5 together. And then last but not least, we need to find the probability that x equals 1. And so probability of 1 is, again, we just sum the joint PMF values that are where we have x equals to 1, and these are P1 -2 and P1 and 2, and when we sum those up, we'll get 0.25. So if you look at this PMF that we just computed, you can notice that x is the same as in example 1. What does it mean? Not only that it has the same values, -1, 0, and 1, but also that the corresponding probabilities of each of these values are the same as the x in example 1. So we already computed the expectation and the variance for example 1, so we just use it here. Now let's continue and look at this example again and find the PMF of y. It's very similar. The only thing is that y does not take 3 values. There's only 2 values that y takes, and that's -2 and 2. And so we need to find the probabilities for -2 and the probability for 2. So probability for -2 is basically the sum of all joint PMF values pxy where y is -2. And notice there's exactly three of these. These are P minus 1 minus 2, P0 minus 2, and P minus 1 minus 2. And so when we sum those up, we get 0.475. The next thing and the final thing is to find the probability of 2. And that's again, we're summing up all these values of joint probability Pxy, where y is equal to 2. And these are P of minus 1, 2, P0, 2, and P1, 2. And when we sum those up, we'll get 0.525. So based on that, we can find the expectation, and that is simply by multiplying the values minus 2 and 2 by their corresponding probabilities. So the minus 2 is multiplied by 0.475, which is its probability, and then the 2 multiplied by 0.525, which is its probability. And so together we sum those products up and we get 0.1. And very similarly, we use the formula again for the variance that is that equals to the difference between the expectation of x squared and the square of the expectations. And so the first two terms, their products, and they basically allow us to find the expectation of y squared, and that is simply by squaring minus 2, which becomes 4, and multiplying it by its corresponding probability of minus 2, which is 0.475, and then squaring 2 and multiplying it by the corresponding probability of 2, which is 0.525, and then subtracting the 0.1 squared, because expectation of y is 0.1, so we get, when we square it, we get 0.01. And when we sum the first two up, we'll get 4, and then we subtract 0.01, we'll get 3.99 as the value of variance of y. And now we need to do similar computations for this example for the product of random variables x and y. And x and y are both discrete random variables, so their product is also a discrete random variable. So the first thing we need to do is determine which values x and y take. And xy takes 3 different values. It can take minus 2, 0, and 2. So we can compute their probabilities of xy equals to minus 2 first, by noticing when we get the product of x and y being minus 2. So if x is minus 1 and y is 2, we get minus 2. Or if x is 1 and y is minus 2, we also get minus 2 as the value of the product xy. And so we sum up those corresponding PMF values and we'll get 0.225. And then we do similar computations for xy equals to 0. And so xy equals 0 when we have x equals to 0 and y equals minus 2, or when x is equal to 0 and y equals to 2. So again, we find in these rows, we find the values of corresponding probability, mass values from joint PMF x and y. We plug those in and we get 0.5. And last but not least, we need to find the probability value for xy equals to 2. Xy equals to 2 when either x is minus 1 and y is minus 2, or when x is 1 and y is 2. So we sum up the probability of minus 1, minus 2, and the probability of 1 and 2. And if you look up in those rows at the very end there, these are, well, not quite the end, but you can see that we have at the beginning, we have 1.25 for probability of -1 and -2, and then for probability of 1 and 2 at the end there, we'll get 0.15. So summing those up, we'll get 0.275. And so now we can also find the expectation of xy, and we just multiply all those three values, -2, 0, and 2, by their corresponding probabilities, 0.225, 0.5, and 0.275. So when we sum up the products, we'll get 0.1, and we can also get the variance of xy by using that same formula that we used before, and we just need to square. So again, we square the -2, it becomes a 4, so you can see the 4 there at the beginning, and then we have a 0 because 0 squared is a 0, and then multiplied by 0.5, it's still going to be 0. So the second term is going to be 0, and the third term is going to be 2 squared multiplied by the probability of 2, which is 0.275. And then of course we need to subtract the squared expectation of xy, which is 0.1 squared. And so we get 1.99 as the variance of xy. Now we got all the information that we need in order to compute the covariance and correlation. So these are the values for the expectations and the variances of variables x, y, and xy. And we can use them in a covariance formula of x and y. So notice when we plug in the respective expectation, we get 0.1 at the end, which is more than 0. So what does it mean? Yes, you're right. It means that x and y are positively correlated. And then we can also from covariance compute the correlation, and then just covariance divided by the square root of corresponding variances. And that estimates to about 0.035. So now recall how we talked about estimation of means and variances, and we need to know the population parameters. We can sample the entire population or check the entire population. We can only pick a part of it called a sample, and so we'll get this random variable known as a sample mean when we try to estimate the population mean, and we get sample variance when we try to estimate population variance. So now, of course, right, there's certain difficulty when using the sample mean as an estimator of a distribution mean mu. So without any additional information, right, we have no way of assessing how close the sample mean is to the population parameter mean mu. So to evaluate precision of the estimator, we could do the following. Because x bar of n, which is our sample mean, is a random variable with the variance bar of x bar n, on one experiment it may be close to the mean mu, but on another it may differ from mu by a large amount. So how precise this estimate of sample mean as an estimator of population mean mu is assessed by constructing confidence interval, and the figure illustrates the concept. So now when we look at the confidence interval for the mean, to assess how good the sample mean works as an estimator of distribution mean mu, we must construct a confidence interval, and its construction is based on central limit theorem. So we assume that our random variables are all independent and they are identically distributed with the mean mu. Then the approximate 100 multiplied by 1 minus alpha % confidence interval for mu is given by this formula. So we already discussed this formula at the beginning of lecture 5, and I said that the x bar is a simple mean, the t value is the critical value of student's t distribution, s is a sample standard deviation, and then n is the sample size. right, or the number of these random variables. So again, right, this is our illustration for the confidence interval, and you can see that t is not the same as a standard normal distribution. There's actually some differences, and the critical values of standard normal distribution are called z, and you see them on the horizontal axis. But the t distribution critical values are called t, and they have two parameters, while z distribution, right, or normal distribution, has one parameter. So now that, as I said, z 1 minus alpha over 2 is the upper 1 minus alpha over 2 critical point for the standard normal distribution, and that the t n minus 1 and 1 minus alpha over 2 is more than z 1 minus alpha over 2 for n that is more or equal than 2. And so for most of the samples, we will have the n more or equal than 2. And also the t critical value decreases to z critical value as n gets larger. So for very large values, starting with, for example, n equals 50, right, when we have sampled 50 points, then they are approximately equal. So as alpha gets smaller, the confidence interval half-length gets larger, and it's important to remember. So here's our example where we have 7 observations from a distribution that's not highly skewed. So it's pretty symmetric with a known mean mu. We find simple mean, we want to find simple variance, and we also want to find 95% confidence interval for mu. So let me go ahead and show you how we do that. The simple mean is easy to calculate. We're just using the simple mean formula that we reviewed. It was listed in the table also. So now you can see here, it's just an average of those values of observations. And we get, when we compute it, we get 2.5 for our simple mean. And then we can get a simple variance. And to get the simple variance, not only the difference, the individual observations and the simple mean, and then square those differences and add them together, but we also divide them by the n minus 1. And because n is 7, we have 7 minus 1. We divide this by 7 minus 1. And when we compute this, we get 2.3 divided by 6, and that's 0.38, and then 3 in the period. And now let's take a look at how to compute 95% confidence interval for mu. To do that, we'll use this formula. And so notice that, as I said earlier, n minus 1 is 7 minus 1, which is 6, and also alpha is 0.05, because we're looking at 95% confidence interval, and 95% is 100 multiplied by the difference of 1 minus alpha. So that means that 1 minus alpha, right, is 0.95, right, and so alpha is 0.05. Then we also need to find the critical value of the student's t distribution with n minus 1 degrees of freedom, which is 6 degrees of freedom, and we know that alpha is 0.05, so we can find 1 minus alpha over 2 and then plug it in and get the value of 2.4691. You can do it in Excel too. You would need to use the t dot in, which is the inverse of the t distribution, because that's a critical value. Alternatively, you could see this link to this table from the NIST.gov, which is also included in your module. So you can look up the link in your module and see the table. And so when we plug in those values that we computed, right, with the value of the simple mean, which is 2.5, and then plus minus the value of the critical value of student's t distribution, which is 2.44691, and then multiply it by the square root of the sample variance, right? Because the standard deviation is a square root of sample variance, the sample standard deviation. So we get square root of 0.8 and then 3 in the period divided by the square root of n, which is 7. And so these are the values for the interval. So we have 2.5 plus minus, and then when we subtract, we get the lower value of the interval, and when we add, we get the upper value of the interval. And this is what you can use to continue working individually on your Lab 3A. Good luck!